before we conclude the external convection, I would like to solve two more problems to show you some more concepts, to clarify some of the concepts that we have already introduced. And once we are done with the external flow, then we will start to concentrate on internal flow. For example, the flow which takes place when there is a heat transfer in a flowing fluid through a tube or a pipe, which is a very common occurrence. There are many such applications where fluid flows through the pipe and another fluid flows through the outside of the pipe in order to initiate heat exchange between a cold fluid and a hot fluid. So, since we have already covered external flow, that is how to treat flow outside of a surface, and then if we can find out the relations or correlations which are applicable for flow through a conduit, then that would enable us for the design of heat exchange equipments that's an indirect heat transfer between a cold fluid and a hot fluid with something in between, which is the first step for the design of heat exchangers. So, as I said, before we conclude our external flow part, I am going to solve two more problems and explain some of the intricacies of external flow heat transfer. So, the problem that I have chosen for this class is about a steel plate which is coming out of the mill at a high temperature. So, the steel plate is being pulled while it is being very hot at a certain speed. So, the steel plate comes out of the hot rolling mill at a very high temperature and it is being drawn at certain speeds. So, the length of the steel plate, the thickness of the steel plate, the temperature, etc., all are provided. Now, as it is being pulled, obviously there is going to be heat transfer from the very hot steel plate to the ambient air which is outside. And considering only convection, that is neglecting the effect of radiation, which ideally should have to be considered since the steel plate is coming at a very high temperature. But since we have not studied radiation yet in this course, so we will for the time being neglect radiation and we will only consider the interaction of the steel plate with the ambient by the convection process. So, as the steel plate is being pulled, it is going to lose heat because of convection. Now, whenever it loses heat by convection, the first thing that we need to evaluate is what is going to be the value of the convective heat transfer coefficient, or H. And from our study, we know that this H is a function of the axial position. Where exactly you are measuring this H, what is more specifically, what is the value of Reynolds number based on length at that point, that would dictate the value of the heat transfer coefficient. So, if I can find the heat transfer coefficient at a specific location on the moving plate, then by applying or by creating a small shell and making the heat balance, we should be able to correlate the heat which is lost and as a result what is going to be the rate of change of temperature at that point. Because as the plate is moving away from the mill, its temperature will obviously start to reduce. So, the rate of reduction of temperature of this steel plate would definitely be a function of what is the value of the local value of the heat transfer coefficient. So, the specific problem that we are going to solve in this class considers if you look at the following figure over here, you have a hot roll section from which the steel plate emerges and it moves with a velocity equal to 20 meter per second, and initially it is at a temperature of 1200 degree Kelvin. So, the temperature is over here is 1200 Kelvin. The length of the plate, that means this entire length is 100 meters and the thickness of the plate is thickness of the plate is 0.003 meter. So, it is only a 3 millimeter thick steel strip that moves with a velocity equal to 20 meter per second, and the property of the steel is given as rho and Cp, the values of which are given, and we will this is exposed to air, the ambient is air, and for air the kinematic viscosity is given as 76.4 into 10 to the power minus 6 meter square per second, and the value of K, the thermal conductivity, is 0.0549 watt per meter Kelvin, and Prandtl number for air will generally be very close to 0.7. So, for this specific problem it is given as 0.702. So, the first assumption that we are making is that radiation and conduction effects these two effects are neglected. And secondly, we would assume that transition from Reynolds number for the flow to become from laminar flow to turbulent flow is equal to 5 into 10 to the power 5, which we have assumed for most of the cases. So, the questions, the things that you have to evaluate are the following. You have to determine the initial rate of change of strip temperature, at 1 meter from the leading edge, from the leading edge, that means over here, which is 1 meter, and at the trailing edge. The trailing edge being at the end of the entire length. So, which is at equal to 100 meters. So, find out what is the rate of temperature at this point and at this point. So, this is at a distance of 1 meter, and of course, this is at a distance of 100 meters. In the second part, which is also equally important, determine the location at which the cooling rate is minimum, at which minimum cooling rate is achieved. So, these are the two problems, these are the two questions that we need to answer. One is at this point, which is 1 meter from the leading edge, what is going to be the rate of change of temperature at that point. So, we would like to, when I said rate, it is the time rate. So, I would like to find out what is dt dx at x equals 1 meter, which is 1 meter from the leading edge, and at the trailing edge, which is at x equals 100 meter. So, these the two values of dt dx at these two locations are to be evaluated. And the second part of the problem is find out the location at which minimum cooling rate is achieved. So, in order to answer this, we again would refer to the behavior of the heat transfer coefficient with distance, as we have shown, as we have analyzed before. And the second problem that I am going to do in today's class would also require the knowledge of how heat transfer coefficient varies with distance and what kind of changes would you expect when the flow changes from laminar to turbulent. So, the initial sharp decrease of the value of H coming to a plateau and then changing to turbulence, turbulent heat transfer, turbulent mode of heat transfer beyond a certain point, that is something which we would like to discuss. But let us concentrate on the first part of the problem. So, the first part of the problem, in order to find out the initial rate of change of temperature, that means dT dx, we need to write a heat balance. The way we are going to write the heat balance is the following. So, we will take some portion of the strip, enlarged view of that, and let us say I am taking a thin slice of it. The area available for the top area. So, if you think of this one, then this area where heat transfer is taking place, we are going to assume that this area is AS, that is the surface area. Since the thickness of the strip, so this is the strip, since the thickness of the strip is very small, we need not take the heat loss from the sides as compared to the width of the plate. So, we are neglecting the heat losses from the side. So, in here there is no heat input, only heat is going out of it. So, if I write my basic conservation equation, it would be time rate of energy coming into the system minus time rate of going out of the system plus or minus generation or depletion is going to be equal to the rate of energy storage. So, this is the fundamental equation for fundamental energy conservation equation in terms of rate. So, rate of energy which is coming in minus rate of energy that is going out plus or minus generation or depletion is going to result in a change in temperature of the object from which these processes are taking place, the result of which will manifest itself as a change in energy stored in the material, and then we would simply express the energy storage in terms of temperature. So, I am going to get a time rate of change of temperature of the material from which energy is coming in, going out, generated, etc. So, for the problem at hand, there is no energy in term. So, E dot in is 0. The only energy, and of course, there is no energy generation or depletion in the system. So, the only this is going to be my new equation, which is d energy stored by dt. Now, what is energy out? The energy out is only by convection. So, and it is taking place from the top as well as from the below. So, the energy out in Newton's law note that I have written H suffix x. The x denotes that we will have the variation of H with axial location. So, this is my x. So, this takes into account for heat losses from both top and below, and this is simply Newton's law of cooling. This must be equal to the energy stored. The energy stored is simply m dot or d dt of m dot Cp times delta t, where delta t is t of the strip minus some T ref, where this T ref is a reference temperature in order to express in terms of energy. So, it should simply be m dot Cp dt by d temperature. So, this is a constant and we will call this as the rate of cooling. Now, this m dot Cp can also be expressed as rho times volume, which is A s into delta. Delta is the thickness of the strip. A s is the surface area. So, my governing equation would simply be times I. So, the time rate of change of the strip temperature would simply be minus 2 h suffix x T minus T infinity by rho delta Cp. So, when you put the values of T infinity. So, T is equal to 1200, T infinity is at 300 Kelvin, that is the temperature of the ambient air. Rho is provided as 7900, delta is 0.003 and Cp is given as 640, all in appropriate SI units. This would simply be equals 0.119 Hx Kelvin per second. So, this is then from your fundamental modeling of the process. This is the expression, and the only unknown that you have to evaluate then is what is the value of Hx, and since it depends on the location, actual location of the point at which you are measuring dT, the temperature variation, the temperature variation with time, the value of Hx at that location is to be evaluated. So, the problem then boils down to finding the value of Hx. We just now have to choose the right expression for evaluating Hx, and we choose the right expression for Hx based on whether it is laminar flow or in the turbulent flow. Therefore, the next step of the problem would be to evaluate the value of the Reynolds number at x equals 1 meter, which is case 1, and at x equals 100 meters, which is case 2, and see whether they are in laminar zone or in turbulent zone. So, the next step of the problem is to evaluate the value of Reynolds number, which we are going to do next. So, at x equals 1 meter, the Reynolds number, the actual value of Reynolds number, which is V times x by nu, where this is the kinematic viscosity of air. So, this is 20 meter per second times 1 meter, and the value of nu is 76.4 into 10 to the power minus 6 meter square per second. This would give you a value of Reynolds number of 2.62 into 10 to the power 5. And of course, as you can see from the value of Reynolds number, this is less than the Reynolds number at transition, which is taken to be as 5 into 10 to the power 5. So, therefore, at x equals 1 meter, the flow inside the boundary layer is in the laminar mode. So, therefore, you need to choose the correct expression for Nusselt number, or in that way the value of Hx based on the laminar correlation of Nusselt number. So, the laminar correlation of Nusselt number in this case would simply be 0.332, 0.332 R Reynolds number to the power half, Prandtl to the power 1/3, and this is H k by d, sorry, H d by k. So, there is going to be k by x, where k is the thermal conductivity and this is the actual location. So, the Reynolds number you have already calculated to be 2.6 into 10 to the power 5. You know the value of Prandtl number to be equals 0.702, and you know the value of k. So, once you plug in these values, and this x is 1 meters into 0.332, 2.62 into 10 to the power 5 to the power half, 0.702 to the power 1 by 2. So, H x is equal to 8.29 watt per meter square Kelvin. So, therefore, at x equals 1 meter, and we are simply going to use the relation that we have obtained before, that dt this is in Kelvin per second. So, this expression we are simply substitute the value of H x and obtain that the time rate of variation of temperature at x equals 1 meter would simply be equal to 0.987 Kelvin per second. So, that is for part 1. Now, let us concentrate on part 2, where it says at the trailing edge. If you calculate the value of, that is at x equals 100 meters, if you calculate the value of Reynolds number, you would see that the Reynolds number would turn out to be 2.67 into 10 to the power 7. I am not doing this, you are going to do it on your own, which is definitely greater than the transition value of Reynolds number, that is 5 into 10 to the power 5. So, therefore, flow is definitely turbulent at x equals 100 meters. Next step is simple. You simply have to choose the expression for Nusselt number, which is valid for turbulent flow, Reynolds to the power 4 by 5, Prandtl to the power 1 by 3, and since it is Nusselt number, I am going to, in order to obtain H x, I am simply going to write k by x, and then put this as before, put the values. Put the same values over here one more time, and you will obtain the value of H x to be 12.4 watt per meter square Kelvin. So, if you compare this value of H x, which is in turbulent flow, with that which you have obtained at 1 meter, which is in laminar flow. So, you can compare and see that in one case the value is 8.3, the other case it is 12.4. Therefore, it is consistent with our understanding that with increase in turbulence, the value of H x is going to be more, and once you do that with the relation that we have already obtained, this dt, this is going to be equal to minus 1.47 Kelvin per second. So, again if you compare this value with the value that we have obtained at x equals 1 meter, since it is laminar, the heat transfer is less, and therefore, the rate of drop of the temperature of the steel strip is going to be less as compared to at x equals 100 meters, which is turbulent, leading to a higher value of H x and a higher value of the temperature drop with time. So, this again shows us, tells us how to solve problems of this, and one of the most important steps in this type of problems is to find out what is the value of Reynolds number. Based on the Reynolds number, you decide about the flow pattern, is it laminar or is it turbulent. So, based on that, whether it is laminar or turbulent, you choose the appropriate relations for Nusselt number and then calculate the value of the value of the heat transfer coefficient or any other value which are related to heat transfer coefficient. For example, here the time rate of drop of temperature at a specific location. The second part of the problem tells us to find out what is the minimum cooling rate where do you think the minimum cooling rate is going to take place. So, if you see in the first part of the problem, we have got a value of H x, and from that H x, the convective heat transfer coefficient, we obtained a numerical value of dt dx at that specific location. And for 100 meters also, we got another value of dt dx. The difference between the two only being that in one case you have laminar flow, in the other case you have turbulent flow. So, the laminar heat transfer coefficient is generally smaller than the turbulent heat transfer coefficient, and if you again think what we have done before, how the heat transfer coefficient in laminar flow would behave, how the transition is going to take place, and how the onset of turbulence increase sharply the value of the heat transfer coefficient, but beyond that point the heat transfer coefficient is going to slowly decrease with increase in thickness, that means with increase in Reynolds number. So, roughly the value of the variation of the heat transfer coefficient can simply be written, can simply be expressed in this form, where you have the heat transfer coefficient H x as a function of x, and it is going to come down sharply and then it increases and then slowly decreases. So, this is the point where you have the onset of turbulence. On this side you have laminar flow, over here you have turbulent flow. So, as you can clearly see over here, the minimum cooling rate would therefore, minimum cooling rate is associated with the minimum value of H x. So, minimum cooling rate is associated with the minimum value of H. Hx. So, the minimum value of Hx is going to be somewhere in this region where the transition from laminar to turbulent takes place. So, just before the transition, that means for a value of R Reynolds number REXC at 5 at equal to 5 into 10 to the power 5, this is the point where Reynolds number is 5 into 10 to the power 5, the point of transition. This is the one which is going to give rise to the minimum value of heat transfer coefficient, and therefore, it is going to give us the minimum cooling rate. So, for Rex equal to 10 to the power 5, you can calculate what is the value of Xc, which would be 5 into 10 to the power 5 times nu by V from RESC, and this would be 5 into 10 to the power 5 into the value of kinematic viscosity, and this would be equals 1.91 meter. So, at a distance of 1.91 meter from the edge, from the leading edge, that means the point at which the steel strip is coming out of the hot mill, that is the point where you are going to get the minimum value of H and therefore, the minimum value of the heat transfer coefficient. So, if we go back to our original figure, we have calculated at 1 meter it is laminar and we got some value of dt dx. At 100 meter it is turbulent, so we got some other value of dt dx, but this is the point which corresponds to, let us say this point corresponds to x equals 1.91 meter. This is the point which corresponds to the transition from laminar to turbulent, and therefore, the transition from laminar to turbulent is associated with the lowest possible value of heat transfer coefficient, and therefore, the lowest lowest possible value of dt the time, the time rate of change of temperature. So, the summary of this problem tells us, first we need to find out what is the value of Reynolds number, what is the flow pattern, choose your relation or correlation accordingly. In some cases, write a simple heat balance starting with the most fundamental conservation of energy and identify the terms which are relevant, express the terms in terms of, for example, in this case the heat losses were expressed by Newton's law of cooling, and you get an expression to obtain either the time rate of change of temperature or any various other quantities that are of interest in practical applications. So, in the next class we will see another problem which is slightly more conceptual than this one, and that would be the end of external convection for this course.